All right, our goal today, you can grab a highlighter. Our goal today is to be able to talk about translation. So what we've been talking about is transcription, going from DNA to messenger RNA. We think about the word scribe or transcribe. It means writing down the message. So we wrote down the message on messenger RNA to send it out of the nucleus. Now we have to go through translation. That's the second step. We have to change this code into amino acids or into proteins. That's the second step. So just like yesterday when you went out in the hallway and you wrote a message and you had to send that message back in here, and then you had to decode it from the symbols to English. You had to translate it. Translating is taking from one language and going into the other. The other thing here is using a model. So when we use any of those dry erase strips that you just used, that's an example of a model, okay? When I have the pictures on your notes packet, that's an example of a model. So on a quiz or a test, I would expect if I have some kind of picture or drawing or representation of what's going on, you can tell me what the different parts are. So translation here. So what I would like you to do is take a second, look at the pictures on this page, and I want you to see if you can chat with a partner about what you see happening. Oh, I see this molecule here. Oh, this is kind of the same as the last picture, but it's a little different because this. So take a few seconds, talk with a partner about what you see happening. So now that we've talked a little bit about, or we've looked at what's going on in this picture, let's talk about what exactly we are seeing. So there are 3 bullet points you're going to fit next to this first box. So just keep that in mind as you're writing. There will be 3 bullet points. You'll notice when you look at this picture, you see a ribosome because the messenger RNA is going to the ribosome. Do we see the ribosome? Okay. We see the messenger RNA. That's the line with the letters. We see something called start. There's a place where it can start, okay? So I like to think about this as kind of like recipes. So if we think about DNA being like a recipe, imagine you've got a cookbook full of recipes. You need to know, where does the recipe that you want start? Our DNA strand is full of all of these different recipes for different proteins. We need to know where to start to make the one specific protein the cell wants to make. So the ribosome is going to start by looking on that RNA strand for something called a start codon. We'll talk about what a codon means in a second, but it's going to look for where to start. So it needs to know what's the starting point on this messenger RNA that's really long and has millions of letters. So if I want to make an insulin protein, I need to know, where does the insulin protein start? And it's going to look for the start signal for the insulin protein. I use the word codon here. We're going to have to talk about what this word codon means in a second. So in a minute here, I'm going to show you a picture and ask you what codon means based on this picture. So let's take a look. A codon. What can you tell me about codons? Group of 3 letters. And it's on what? 3 letters on? RNA, messenger RNA. So a codon is just 3 letters. And the 3 letters are coding for the building block of a protein. Anyone remember what the building block of a protein is? Amino acid. So each 3 letters codes for one building block, one amino acid. So we're going to write down that definition. A codon is a set of 3 mRNA letters or bases, because remember the bases are letters, that code for an amino acid. So when we say a start codon, we just mean the 3 letters that code for start. That code that tell the ribosome to start making that protein. So it has to know, there's a whole bunch of letters. We have to know, where does the ribosome going to, which part of that DNA is it going to start at to make that protein? So there's a protein code, and then another protein code, and another protein code, and it knows which protein code it's looking for to start making that specific protein. So what 3 letters are at the beginning there? where it says start on the picture? AUG. Yeah, so AUG are the 3 letters that code for start. In parentheses, what you see is this word methionine. That's an amino acid. So that's the first building block. So the 3 letters AUG code for that first building block. And it's the first building block for every single protein. Doesn't matter if it's a protein in your hair, in your blood, in your skin, in your nails. All the proteins are going to start with the 3 letters AUG for the messenger RNA. And then the proteins themselves start with the building block amino acid called methionine. You might be wondering, Ms. Frankson, how in the world does AUG code for methionine? How does that work? I don't understand the code. It's not my language. Let me show you. So I'm going to have you flip in your packet to find this chart. It's a circle. So how do we know that AUG codes for methionine? We use this circle chart. Now, this circle chart is not something that the cell uses. The cell is not like, oh, let me check. I'm going to whip out my circle chart. Okay, the cell does not do that. The cell knows all of these things. Scientists, however, don't know these things. So scientists made this chart to help them. So here's how this works. The first thing we have to do is we have to find the first letter in the inner circle. What is the first letter? A. Okay, so I have to find A. So once I find A, notice how A is only 1/4 of the chart. There's like the 2 lines there that kind of delineate where A is. We're going to block off all of the rest of the chart. We're not going to look there. Then what I'm going to do is I'm going to find my second letter in the second circle. What's my second letter? U. All right.
Then it's G.
So I'm going to, yes, exactly. Then it's going to be G. So I'm going to find U. Notice I find U. See how my line here, right there, U, I'm going to block off everything that's not part of that U. And then I'm going to find my third letter, which, Riley, what's my third letter?
G.
G. So I'm going to find G in this third ring and see how it codes for methionine. So that's how we know which letter codes for what. So what I would like you to do, because this is where we start all the time, I would like you to write start next to methionine. Or you could highlight it or write a star or something on your chart, because this is where we're starting with all of our codons. All right, excellent. So let's do one more. AAC. Okay, find A in the inner circle. Okay, so we find A in the inner circle, block everything else out. The next letter is A, so find it in the second circle. Okay, and then the third, and block everything out. And then my third letter is going to be C. And so we're going to end up coding AAC asparagine. Okay, so AAC asparagine. So what I would like you to do, flip to this page in your note packet that has these. If you were gone yesterday and you don't have these letters written down, feel free to copy them down. I need you to add lines in here because remember we said a codon is 3 letters. So add a line after each 3 letters. So AUG, GUC, UUC. And then we need to put these letters in our codon chart to see what they code for. So we have AUG, and we're going to look for what it codes for. And we're going to write it down. Now, here's the deal. Scientists are lazy too. Notice how all of our amino acids have big, long, fancy names. Scientists abbreviate them a lot of times with like the first 3 letters. So for example, methionine would be MET. And isoleucine would be ISO. So feel free to abbreviate because they're kind of annoying. Okay, so you're going to use your codon chart and you're going to fill in. So you're going to put in AUG in your codon chart, see what amino acid it codes for, and write that in. All right, so let's go over. You should have gotten methionine. Now, as I said, scientists are lazy and they like to abbreviate. So you're always welcome to abbreviate using the first 3 letters. So if you wrote MET for methionine, great. Okay, then we have valine, VAL. okay? And then we have phenylalanine, PHE, okay? In our second example here, I accidentally included an extra letter. Just ignore that last U at the end. But we should have methionine because that's our start. Lysine, or LYS, and then serine, SER. Okay? So now that we know how the messenger RNA codes for amino acids, how do those amino acids get there? So around our codon chart, those are all amino acids, but how do they get there? What I would like you to do is you're going to flip back to your notes. So on our chart here, on that second box, we're going to write that there is something called a tRNA, another type of RNA. It's called transfer RNA. It's going to bring our amino acids to the ribosome. It's going to carry them. Remember, amino acids are building blocks. On this picture, we see it kind of looking like a puzzle piece. But now that the tRNA knows this code, the cell knows this code, the tRNA, the ribosome knows this code, they don't need a fancy chart. They're able to just do this and bring the right amino acids. Now, the order of the amino acids is going to determine what protein we have, just like the order of the bases in DNA determines it. If I'm making a chain and I've got blue, yellow, green, that's different than blue, 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 yellow, right? If those are my building blocks and I'm just using colors, okay? So how does the tRNA know the code though? How does it know which amino acid to bring and where to go? What I would like you to do, we're going to do an activity where you head to your lab table, okay? At your lab table, you have your messenger RNA that you did previously. We're going to put your messenger RNA in this piece of paper here, and I want you to see if you can figure out where the tRNAs go. Good. So our question of how do we know where these tRNA cards go? Well, they matched. You could have used that you knew methionine was the first one. And if you look, methionine is the amino acid up at the top. It's matching A with U with A, and G with C. So the rest of them are going to match in here too. And all of their letters are opposite. It's one giant matching game. So that's how the tRNA, that's how we know which amino acid to bring, is all based on this code and matching letters. We have a special name for the three letters at the bottom of the tRNA that match. We'll talk about that in a second. But what I need you to do is go back to your, you can bring your green strip, erase it, put it back in your Ziploc, and then go back to your seats. So the tRNA has three letters. They match up with the RNA, but those three letters on the tRNA are called an anticodon. That's how the tRNA knows where to go. So we have a couple more bullet points, one bullet point for each of the remaining boxes. And then we'll be done. So when we're bringing an amino acid, we bring an amino acid, but remember that's one building block. They have to be connected together to make a protein, just like kind of how nucleotides with DNA have to be connected together to make that double helix. So we have to connect them together. There's a word that we already know that connects them together, and those are the peptide bonds. And you can see in that picture, we have the peptide bonds labeled. So we're going to connect them together. They're going to be dropped off.
Okay.
Eventually, the T for the tRNA is going to go fly away. It's just going to leave the protein. So this tRNA is going to go away and only the protein will be left. And then we're going to keep going until we reach stop. So there's three letters that code for stop. We all good? So we're going to turn our sheet sideways then. And we're going to write down that this whole process is called translation. We're translating the letters from the messenger RNA, the base letters, into a new language, the language of amino acids. So translation is converting mRNA into, you can either say amino acids or proteins, either one. And what part of the cell is all of this happening in? The ribosome. So remember, the first one started in the transcription